Pre-calculus friends, we're in section 1.7 and we're taking another look at the problem number 3 that kind of referred to the example in the beginning of the chapter. And so we're looking at this information. We want to graph the tax bracket for different incomes. And we said this kind of has a piecewise function kind of vibe, right? So it does have that because we're looking at different domains really for each part of the function. So we have a specific tax bracket for a different interval of taxable income. So we're going to definitely represent those intervals on our x-axis, and then we're going to graph the corresponding tax bracket. So I've made my corresponding x and y axis to correspond to the data that they've given us, and now I'm just going to go through and graph. So at 15%, we know that from 0 to about 25,000. So each of these tick marks is about 25,000. So from 0 to 25,000 and just a little bit beyond, we are in a tax bracket of 15%. And so that's what that would look like. But as soon as you get beyond $25,350, right? So let's say that's around right there. As soon as you get beyond that, you are now going to be charged in the 28% bracket. So that brings you all the way up here, and it's going to start a little bit after 25,000, and then we're going to move on until we get to 60,000, which is going to be somewhere after this 50,000, right? So then as soon as you get to 61,401, so it stops there, and the next value, we're going to jump to another tax bracket, which will be 31%. And that 31% tax bracket is going to take you all the way past the $200,000 mark, $225,000 mark, and just a little ways beyond. And as soon as you get past 128,000, I don't know if I said the right thing last time, but you know what I mean, $128,100. As soon as you get above that, boom, you are into a new tax bracket, which is 36%, which is going to be just above there. And then we're going to move all the way. That's going to last all the way until we're in the 200,000s, a little bit closer to 278,000. And as soon as you pass that mark, boom, you're almost at 40% taxable income as soon as you get to $278,450. $451, I guess, $450.01. I wonder how specific they are. And so we see that we have this situation like that. So yes, this is a piecewise function because there's different pieces to it, but honestly, this piecewise function is definitely in the category of a step function, as all of the graphs are horizontal and it kind of has steps. They're not evenly spaced out, but they are steps. In example 4, we're going to be graphing an absolute value function. Now, there's lots of ways to try to figure out how to graph these best. And honestly, the best way is if you remember parent functions and you know how to graph in that way. But if you don't, honestly, you can always make a table and plug in values. And what you're going to be looking for when you plug in values is a turn. You're going to be looking for where the graph starts in one direction and then turns and you get the same exactly f of x values out. What am I talking about? Well, let's see. Let me just throw some numbers in here. Let's do -3, -2, -1, 0, 1, 2, 3, and see what happens. So when I plug these numbers in, when I put in our -3, I end up with a 0, right? Because -3 is going to be positive. 2 times a positive 3 is 6. 6 minus 6 is 0. When I put in a -2, I end up with a -2 back because I get a positive 4 there. You guys see what I'm doing, right? Right, okay. So then I'm going to end up with a -4 here. When I put a 0 in, I get a -6. When I put a 1 in, I get that -4 back. This is going to be a bending point, right? This is where, it's going to be, I see. So what's happening here is that I'm actually going to get the same values in my output given the values of my input because I found that bending place, all right? So what I'm going to do is plot these points. So at -3, I'm at 0. -2, I'm at -2. -1, I'm at -4. At 0, I'm at -6, which would be down here. And then everything else is the same going back up. And since I know that this continues on forever, I can draw lines like this to indicate, you know what happens. We just make it a little bigger. Okay. So this is what my graph would look like. Now, there's a number of ways to graph these guys. This is like the most rudimentary way, but we can also look at this. We remember that f of x equaling the absolute value of x per se is, let's graph this in a different color, is just going to be this perfect V like that. And then this too is actually going to stretch or make more narrow the graph. And this -6 will make it drop down to 6. So what happened here, if you guys remember, if not, that's okay. We got a narrower graph, but then it dropped down to -6. That's what the -6 does, gives us that translation down there. And that's how we came up with this graph. If that does not make sense because you've never seen parent graphs and translations of graphs, that's definitely something we want to cover and talk about. So you guys can give me some feedback and let me know if that made sense. If not, definitely plug and chug. Go ahead and plug in the points so you can graph your function. In this final example, we're going to be identifying the type of function that models each situation. Then we're going to write a function for that situation. So part A, manufacturing. The stated weight of a box of rice is 6.9 ounces. The company randomly chooses boxes to test to see whether their equipment is dispensing the right amount of product. If the discrepancy is more than 0.2 ounces, the production line is stopped for adjustments. So the answer is kind of already here. But let's just talk about what's going on. So we have this situation where the goal is to have 6.9 ounces. And of course, sometimes we go left and right in terms of we can have a little bit more or slightly less. And so what this equation is, and I'm going to zoom in on it a little bit for us, what this equation over here is showing us that the difference between the actual weight and the weight of the supposed weight of the boxes of rice has to be within a particular minimum. And so we want that weight to be equal to or less than a 0.2 ounce difference. So we want it to stay right around here. We don't want that difference to be more than that. And so notice, since there's absolute value signs, we know that it can be positive or negative 0.2. Let's think about it specifically, meaning they will allow it to be as high as 7.1 ounces or as low as 6.7. But once it's out of this decent range, let's say, that's when their equipment would be stopped. So the function that we can look at is that the weight, we're looking at 6.9 minus W as the possible values for what we would tolerate, or looking at what values we would want to tolerate. So in part B, we're looking at a certain telephone rate plan. The price of a cellular telephone call is 35 cents per minute or a fraction thereof. And so I think we can have kind of an understanding of this. If you don't make a call, then it doesn't cost anything. But as soon as you make a call, even if you don't stay on for that full minute, it's going to cost you 35 cents. And then everything after, we just keep popping up. And you can see this is a really good example of a step function. And so how can we relate this into the fact that we know y is equal to this guy is the greatest integer function that we've used before. So we're going to use that to describe this situation. So if we start off thinking about the cost per minute as a function, and we say, oh, well, maybe it's equal to the greatest integer function, like that. And then add the 35, since it's 35 cents per minute, or 0.35. This seems like it could be reasonable, but if we start putting numbers in here, let's say 0 minutes, 0 minutes would cost nothing. 0.5 minutes would also cost nothing, and that's not what we want. We actually want to charge, if this were our company, we want to charge for all the minutes leading up to that actual value. So for instance, the first part of this, we're going to write this as a piecewise function. The first part of this is we need to establish the fact that, yes, we do want the function to equal this 0.35 times the greatest integer that's equal to or less than m, as long as this is the number of minutes. So every time the greatest integer function is equal to the number, the actual X value per se, like every time that happens, we want to be charged 35 cents. So that's only giving us these dots here, that first part. Now we need to find a way to establish the fractional values, rounding the fractional values up so that we can get all of this mapped to the same 35 cents and 70 cents and so on. And so what we would say now is we could look at that as 35 cents plus the greatest integer that is greater than or equal to m plus 1. And we would do this if the greatest integer of the value of the greatest integer of m is less than m. So now we are getting to round it up. You guys see, we're rounding up those values when the value isn't quite equal to the integer that's coming up. So that's the kind of a function that we'd have to use and to represent this situation. I know that wasn't very easy or straightforward. Please let me know if you have some questions about this, because, you know, it takes a little bit of practice kind of thinking about these types of problems in this way. Look, I look forward to talking to you guys soon. Please, please take care. Bye-bye.